So, good day, everybody. Thank you for inviting me to this workshop. So, my talk is going to overlap to some extent the previous talk, but I'm going to put the emphasis more on MPI than OpenMP. So, just a bit of introduction. I'm the coordinator of the hardware topology working group in the API forum. And I'm also a member of the group that develops the HW log software that Helen mentioned in her talk. So as Helen mentioned in her talk, so parallel computers are increasingly complex. You have a trend to increase the number of computing nodes, of core counts, and this also has the effect to you have more hierarchical systems with a lot of levels in your memory. So one effect of this complexity is performance heterogeneity issue, meaning that depending on your process or your MPI process location on your system, you're going to witness a difference in performance. So for instance, if two processes are locating within the same NUMA node, you're going to have a best performance as opposed to processes that are belonging to different packages or even to processes that belong to different machines. So one motivation of what I'm going to present is that application developers need abstract features to deal with these hardware characteristics. And they have also to deal with very low-level existing tools, such as HW log, which was mentioned previously, and also Mercier. So they have to deal with both these hardware details and these pieces of software, which are not always easy to understand and to manipulate. So I'm going to make a quick introduction about MPI and its programming model. So MPI has been widely used for parallel application programming since the mid-90s. It's a great success in parallel programming, and it relies on message exchanges between processing entities, which are called MPI processes. And interestingly, MPI processes are not defined currently in the MPI standard itself. The programming model is flat, which means that any process can communicate with any other process, and there is no routing scheme in the programming model, but a routing scheme could be implemented internally by the MPI library. And originally in this model, there were no notion of locality or hierarchy. One interesting feature of MPI is that it's hardware agnostic, meaning that it makes no assumption about the underlying hardware, but it does not mean that you cannot access hardware details at the application level. So there have been some additions to the standard since the first version. You had a routine called MPI get processor name, and now you have several features in the current latest version of the standard, which is a 3.1 version, which are virtual topologies, neighborhood collective communications, and some shared memory support. So virtual topologies express more communication pattern for your application. So it's more a software locality. The standard explicitly states that the virtual to physical mapping of processes is outside the scope of MPI. However, hardware can be taken into account because some routines feature a reordering parameter, and when you trigger this reordering, you can possibly match your communication pattern to your hardware topology. However, this feature is implementation dependent, meaning that it's not standard, and you don't have any guarantee that when you switch from one implementation to the other, or even worse, when you switch from one version of an implementation to the other, you're going to have the same behavior. Also, there is a chicken and egg problem with virtual topology because implementation do not do a good job of implementing these features, so people tend to not use it. And if people do not use it, implementation are not going to do a good job about it. Neighborhood collective communication leverage virtual topologies too. A virtual topology can be attached to a communicator, and once again, it represents the application's communication pattern. And this communicator can be used for the NTC functions. And users can define their own communication pattern for collectives, so they have a better control of communication and their scheduling. And this feature refines, to some extent, the flat programming model, the original model of the MPI standard. It improves scalability and locality. So shared memory support is also part of what is currently available. So until 3.0, the shared memory support was hidden in the implementation, meaning that user didn't have any control about it. If communication with shared memory was faster, the implementation was likely to use it, but user could not control this. Now, with the advent of hybrid programming, MPI plus X, it's very commonplace. For instance, Ellen talked about MPI plus OpenMP with, multi-threading your MPI processes. You can also do MPI plus MPI with this approach. Message passing for internet communication, and do MPI shared memory for intranet communication. So how can you do that? You can use a function called MPI complete type with one specific value, which is com type shared, to isolate your processes on computing nodes. And then with the function MPI win allocate shared, you're going to create shared memory windows between those processes. As a result, you're going to have an explicit two-level hierarchy in your application, meaning that you can bypass completely the MPI stack, and you can use load and store operation instead of send receive. So you can take advantage of the performance discrepancies I showed earlier in my talk, but not all the levels within the node are leveraged. So you can use another programming model. So I'm going to show you what is going to come in MPI 4.0 with regard to hardware topologies management. So I struck out the first item because it had not been voted in yet. So I'm not going to talk about it, but it was there was some discussion about this feature to optimize Cartesian topologies. So I'm going to speak briefly about sessions and put the focus on hardware communicators. So the original goal of sessions was to solve composability issues when you have several layers in your application, and each layer does an init of the MPI library, and the other part of the application doesn't know about it. So the principles of session is to isolate processes in sessions, and there are no communication between sessions. Sessions are very lightweight objects, even lighter than groups, which are already lighter than communicators. And when you have those light objects, you can create groups from them, and then you can create new communicators. And there is a world model which is meant to ease the transition to the real session models. And there is a possibility to give names to sessions which are universal resource identifiers. And it's to some extent, it's an extension of MPI get processor name. So for instance, you have here a job, and which is your whole application, and you can see that you have two different applications, two coupled applications, ocean and atmosphere, and composed of processes. And as you can see, you can have names for physical location of your processes in your system. So it could be used to manage hardware locality and hardware topology management. So now I'm going to explain you the work we did about the creation of hardware communicators. So the purpose of those communicators is to create objects that convey the locality / sharing of resources between MPI processes. So I'm going to give you an example. For instance, you have this machine, which is composed of two packages. Each package is composed of two dies, and in each die you have NUMA nodes. And let's assume that you have one process per core. That is your original communicator. Now we're going to create new communicators corresponding to the physical, to the hardware resources in the machine. So when you split your first communicator, you're going to create two subcommunicators, one for each package. And now each subcommunicator can be now split into subcommunicators, one for each die. Then you do this recursively. You have subcommunicators within subcommunicators for the NUMA nodes. And finally, eventually, you have one communicator per process. So in order to do this, we propose to extend the same function that allows you to create shared memory regions, and that's COM-split type. And we introduced two new types, COM-type hardware unguided and guided. So unguided, you just leave the application, the library is going to do exactly what was shown in the example. So you split at the next level, and guided with an int that is conveyed by the info object, you can split at a very specific level. Now let's see an example. So for unguided, you can recursively, for instance, in this example, you can recursively split your MPI COM-world communicator into subcommunicators. So this code typically is going to do exactly what was shown in the example. And I'm going now to show you a guided example. So in guided example, so you have to set up an info object, and you specify the level at which you want to split. So this level, this name, in this example, NUMA node, is implementation dependent. So I'll be back to this later. And then you do the actual splitting operation. And so when you do that with those couple of lines, you can effectively create communicators that correspond to NUMA nodes. So we did some performance evaluation of this mechanism, and in a very specific application, which is a hierarchical matrix multiplication. And the original matrix multiplication featured some groups that were hierarchically organized, but they were not corresponding to hardware resources. So the last column on the right, excuse me, shows that we managed to decrease the communication time. Of course, the processing time is still the same, but it definitely shows that you can have some performance benefits by taking into account your hardware hierarchy. So we're going to we're still, so this has been voted in the MPI, in the 4.0 version of the standard, which is going to be available at the end of the year. And we still are working on the next versions of the standard. So as I explained earlier, the names that you propose for do the guided split are implementation dependent. This was done on purpose to avoid to introduce name into the standards that could become obsolete or be deprecated if constructor decide to change the name. For instance, the socket name is not very used anymore. It's been replaced by package. So we want to propose some functions so that the user can query what names are available on their system, and they can use it confidently. And also, we want to work also with other communities, HPC communities. For instance, we want to interact with OpenMP communities. So in the previous talk, you've seen that there are a lot of tools in OpenMP that can allow you to control the placement and the affinity of threads. And we want to work with the OpenMP people so that we have a more holistic approach. And as was explained before, process mapping and binding is really a mess, and it's a very complicated topic. But we want to launch. We started to launch some discussion in the MPI forum about that because right now nothing is standardized in this in MPI. I think it's a big problem for people when they want to launch their application. And the CEA, the French Commission for Atomic Energy, set up a dedicated working group, which is currently outside of the MPI forum, but it's a more global approach. It's the target is the whole HPC ecosystem, not just MPI libraries. So we are working in this working group just to make proposals and to see how we can propose a standardized mechanism for mapping and binding of processes and threads. And that's the end of my talk. Thank you very much, and I'll take questions if you have any.